Groovy. All right, so in principle, at the highest level, there are three kinds of calibrations that happen after we launch. The first is we apply and assess our pre-launch instrument calibration. So these are the kinds of things you heard about from Eric and Lorraine and Brian on behalf of Otto. What do you do in the laboratory to understand and characterize your instrument before it launches? All of its behaviors, why we go into the thermal vacuum and things like that. The two others are generally unrelated. The first is a temporal calibration. We want to understand instrument performance as a function of time, and I'm not just talking about on a daily cycle, but on decadal cycles. And then there's the absolute system vicarious calibration. For temporal, we're referencing the sun or the moon. For absolute, we're generally referencing something on the Earth's surface. That's not exactly true. You could vicarious calibrate to anything, but the reality is that you're calling something truth for better or for worse and trying to reference that. It's a final single gain adjustment, and we'll get into what all of this means in detail a little bit later. Just understand that at this point, it is a single final spectral gain adjustment. So, fact of life, sensors degrade on orbit. Solar calibrations happen, lunar calibrations happen. For solar calibrations, really what you're doing is looking for short-term stability of your instrument. OCI has 3 solar calibrators, as you learned, but 2 are going to be used for temporal calibration. Those 2 are identical. One will be used daily. The other identical one will be used monthly. The reason for the second one is to track degradation of the first one. First one's getting exposed to the sun every single day. The monthly one will be once a month, and so by doing so, you can actually get some sense of how their performance is changing over time. Then you have the lunar calibration. This is intended for long-term temporal calibration. It was conceived of in the CWIS era, and everything since then that at least NASA has touched has had to make use of a lunar calibration. And there were actually some battles with the JP, I think it was the NPOS program at the time. But nevertheless, a lot of the early 90s, mid-2000s instruments that were getting ready for launch had not budgeted a lunar calibration maneuver with their spacecraft. And it was something that we actually had to really, really fight for. The lunar calibration is a relative calibration. And what I mean by that is we arbitrarily assign the first measurement or launch or whatever is time 0. And then everything else is relative to that. If you're lucky, you get one good observation per month. Sometimes it doesn't work out. But nevertheless, this is important because of this. So this is the CWIFs, the first decade of CWIFs. The different colors represent the different bands. It goes from blue to near infrared. And just want to point out here, look at the magnitude of degradation of the 865 band. Why is the 865 band important for ocean color? It's not used in chlorophyll. Aerosol? Nope. Atmospheric correction, yeah. So you use the orange band and the red band for atmospheric correction. Look how fast it degraded in the first year. Now MODIS didn't have this problem. MODIS had a blue band problem instead. So everybody's a little bit different. But nevertheless, if memory serves, there was no real good way to do solar calibrations for CWIS. I don't believe it worked. But this is why we do a lunar calibration. You don't use the solar calibrations to do these long-term adjustments. They're frankly just too noisy. All right, so how do you use the moon as a reference? The United States Geological Survey has their ROLO Observatory, the Robotic Lunar Observatory. And what that generally is that they have a physical observatory that has observed the moon. And here's just a series of papers with the names that are, the founders of all of this, Hugh Kiefer and Tom Stone. And what they did is they basically created a spectral model from all of these observations. And so there's a fairly accurate spectral model of the moon that we are using as our truth here. And so the spacecraft performs a maneuver so that the field of view of the optics actually sweeps across the moon. And for CWIFs, that image looks something like this. So you are comparing the radiance measurement here to the model of the moon. And actually, you can see that it does work. It gives you a pretty strong relationship. So the Lunar Maneuver for pace, I think, is really just, I'm not positive, so don't quote me on it, but I think it just might be a roll. So did, Brian, do you know? Is it just a roll to look at the moon and have the scanner sweep on it? I had some images, but I didn't think we could show them.
I'm not sure whether you call it a roll or,
Yeah. It adjusts itself to look at the moon. So Gary's yoga, now we're doing kind of something like this. And you sweep, basically you're sweeping across the moon like that. In the case of, just to give you some context for what this might look like if you were a multiple detector instrument like BEERS, where you're still a scanning instrument that can sweep across the moon, but you have multiple detectors, you'll get something that looks like that. I still think it's kind of cool to look at because it's a view of a moon from our ocean color and atmosphere instrument. This is just a little quick aside. One of the reasons that we did not want PACE to be a push broom instrument is because of lunar calibration. So remember, what does a push broom offer you? What's an advantage of a push broom instrument for a really dark surface?
You get better spatial resolution.
Absolutely, yeah. And why is that?
It has more detectors, like
And what's the advantage of more detectors?
more photons.
More photons, yep, exactly. So you're all right there. So that's really cool. But we now would have to apply a lunar calibration to all of those detectors, right? So instead of having one detector, or in the case of VEERS, a series of detectors that sweep across the moon, you have this two-dimensional CCD array with a bigger field of view. And we figured out that you'd have to do some kind of maneuver like this to actually get every science pixel touching the moon's surface. And this becomes a somewhat complicated pointing exercise for the spacecraft and the instrument. So I just found that to be interesting. I don't know that there's too many other groups in the world that actually worry about push broom instrumentation sweeping the moon.
At some point, I'd like to explain how Part 2 is going to do it.
I did have a video that showed it, but
And let's say
yeah.
quickly, because Part 2 is a push broom,
Mm-hmm.
but we need a combination of solar and moon. So what happens is that when we do a solar, we put a diffuser across the image, and we check the flat field, that everything across the image is as we expect from pre-calibration. We adjust all our individual detectors from this diffused light from the sun. So when the moon ends up in the corner of the image, like this, we can mathematically cross the whole image.
Is that how it's going to work now? Yeah. Oh, awesome. Okay.
I mean, and just so you're aware, the moon is not, there isn't a radiance standard for the moon. You know, if you're making an image of the moon, nobody knows how bright each little piece is. They know how bright the full disk is. It's an irradiance standard, not a radiance standard.
Right. It's a singular value
Yes.
for the surface, which is why we do it at certain phase angles of the moon as well. Meaning you do it when there's a certain size of the disk in geometry. So just a quick example, then we'll move on from this, from VEERS. So this is actually fairly modern. The 4 plots are all for different wavelengths. So there's the first 4 here, 3 more here, and 1, 2, 3, 4 more here. This is just to kind of give you a sense of what a real time series, modern time series look like. And the lines are the corrections that are being fit to it. So lunar calibration happens, and this is basically just the general flow of how the OCI cadence of temporal calibration will happen. QVD, in this case, we're just talking about the 2 solar diffusers. So you have the information from the solar diffusers that come into a correction factor, called the F factor. Those correction factors actually feed into the lunar calibration process. They get combined somehow, and you have a temporal calibration lookup table. So just something for you to take home. Okay, so on to system vicarious calibration. So in this case, it's an absolute calibration. So it's an absolute number, not a relative number. It's a, so it's a gain like a 1.03 or 0.97 or something like that, where no adjustment would be unity or 1. And it actually accounts for the instrument systematic biases as well as the atmospheric correction for ocean color. So let's poke at that just for a second here. So let's just say our target is something on the sea surface. I didn't want to put in an eye chart for the exclusion criteria process, but you have, let's say, one matchup with your target, okay? So right now you have a measurement at the bottom of the atmosphere and you have a measurement at the top of the atmosphere. And in this case, the exclusion criteria are like, has to be collected within 1 hour of each other. The pixel has to be a 3x3 box with nothing flagged or masked. You know, there are other statistics for heterogeneity and homogeneity and things like that, but ignoring the exclusion criteria for a second, let's focus on the process. So either this has to get propagated to the sea surface or this has to get propagated to the top of atmosphere. It used to be we would iterate and bring it down to the sea surface, and we could debate this endlessly, but the way it has worked for 2 decades at this point has been we take the atmosphere correction information from a forward atmospheric correction and then use that diffuse transmittance and other atmospheric properties that we need to propagate the measurement here to the top of the atmosphere, okay? And there are bidirectional reflectance distribution effects that need to be accounted for. There are other things that need to be accounted for various times of day adjustments and so forth. But the take-home message is the atmospheric correction retrieved values are the ones used to propagate the surface value to the top of the atmosphere. If we could fly at the top of the atmosphere all the time for this calibration in, say, some supersonic aircraft, it would be better to do everything at the top of the atmosphere, and then you can ignore that atmospheric correction process. Any questions on that? And Amir, anything that I missed?
The only thing is we do the NIR calibration separately.
Oh, I'm getting, yep, next slide. I am borrowing heavily, almost exclusively, from Brian Fans's 2007 paper, so if you want to doze off for a little while, then just read it, because all of the figures are from his paper. Okay, these are our Vicarious Calibration sites right now. 2 in the southern oceans. I don't actually recall if we're using both or just the South Pacific at this point, and we're definitely still using MOBI. So what Amir was alluding to is that we do this calibration as a 2-step process. The first, we do the NIRM for red bands, and in this case, I think we're definitely only using the South Pacific gyre, so you can ignore that circle. The way this works in principle is you apply the black pixel assumption. So at this point, we're saying that there is no water leaving signal in our 2 CWIFs NIR bands, and I'll use CWIFs as the example. So in this case, we're talking about 765 and 865. So all the contributions are from the atmosphere, surface reflectance, all things like that. So you remove all the things that you can, so you can calculate glint. Sorry, we avoid glint. You can calculate white cap refraction, you can calculate Rayleigh, all the things that Amir talked about the other day, so that the entire signal in these 2 bands are the atmosphere, the aerosols, atmospheric aerosols. But now you have to make a choice. You have to make an assumption. You have to actually make a couple. The first is you have to say to yourself, I know what the aerosol model is, because we're way offshore, we should have a nice maritime aerosol, something like that. And then you have to set one of the gains. So what we do is just assume that the gain for 865 is 1. And then you can run that process that I just described and calculate a gain for the 765 band. So the end result of this is you have 2 gains, one that we're assigning and one that we're calculating. And we'll show you what plots of all of this stuff looks like in a second. The visible vicarious calibration happens next, and we have used the marine optical buoy since like 1997. This requires some truth measurement at wavelengths of interest. So we'll talk about this later, but this doesn't have to be MOBI. It is wonderful that it is MOBI because it is a hyper-calibrated instrument. It's been in the water a long, long time, has a great team of people there. But in principle, you could use other satellite measurements. You could use anything that you consider to be, in quotes, truth. So quickly, marine optical buoy here. It's maintained by the University of Miami, Moss Landing. 20 miles off the west coast of Lanai. You can see that it's a 3-armed instrument with a nice spectral range. And the reason that hyperspectral is really important here is that you can convolute the bandpass of every single instrument you want, because CWIS doesn't look like MODIS, doesn't look like VIRS, doesn't look like something else. But if we're hyperspectral, you have all the information you need to focus on the spectral regions that you actually care about. Now another thing, another religious argument we could have here is this the right measurement system to do this? If you start thinking about in-water optics and uncertainties and questions you might have about a fixed mooring versus a profiler versus whatever, for another time, but planting the seed on, for your future on what you think you might do if you were to design a system from scratch. Nevertheless, this is our source. Okay, so we go through the process of calculating individual matchups for all the good coincident scenes we can find. So what that means is every time the satellite overpasses first the little flat part of ocean in the South Pacific and then over Moby, we decide if it's a good matchup. We apply all of our exclusion criteria to that. We look for the perfect 3x3 box. We throw away the rest. So we're throwing away a lot of data, either because of clouds or because of some failure that triggered a flag or mask. But in general, you just start over time accumulating these matchups, which you can do faster for a tilting instrument than you can do for a non-tilting instrument, given the latitude here. Latitude's in the tropics. Moby's near Hawaii. But we're throwing away a lot of data because we only want to use the best possible data for this calibration. And what we have found is that as you start accumulating matchups and you look at the standard error about the mean, there does become a convergence point over a number. And in the case of CWIFs, our comfort level was right around here. It took on the average 40 in this example case study to get to a point where we were confident we had stabilized our gain. So if they average, say, 20 matchups per year, we're talking about really a multi-year process to get to a game we're comfortable with. Now, that doesn't mean we don't apply a system vicarious calibration game early in launch. We will apply one within a few months of launch to the best of our ability, but this is one of the reasons that you'll find that we reprocess our data fairly regularly. And what reprocessing means is basically you take everything you know that you didn't know the first time you went through the data processing sequence, you apply that, and then you start over. It drives our principal investigators bonkers because they will be ready to submit a paper discussing a time series, and then we're like, we're reprocessing. And then the phone calls come in and the emails, can you wait until this gets published? Happens over and over again. We feel really bad, but once you know how the sausage is made, it really, really hurts to know something's broken and you haven't fixed it yet. But what'll happen in the cadence of something like PACE is, oh, sorry, Lydia.
Is there just one movie?
That's an awesome question. So yes, today, well, two-part answer to that. There is one Moby in the field, and the group actually has 2 or more. They will deploy it for 6 months with a pre-calibration. Then they will take their huge vessel out with a second one, pull the one out of the water, put the second one in, take the one that's been in the water back, and do a post-calibration. And this kind of gets into the how do you treat the gains in a reprocessing sense too, because for something like PACE, we will more than likely be using a Moby-like system. It might not be in Hawaii, but for these long duration deployments, you have the pre-cal and the post-cal of the truth instrument. Now, we've written into all the contracts, I want the data in as near real time as possible. And that's not going to be like 3 hours, but it might be once a week we get a data dump. So let's say we get 6 months of these data dumps, we come up with gains, but then now the instrument team from the field has gone in and reprocessed their data with the post-calibration. We would probably end up recalculating our gains and making a decision whether or not they're different enough that we have to do something with it. But the short answer to your question is, right now there's one. And that's another religious discussion in the field. If you had a network of these things, is that better?
Why don't we use the soul for,
Boussole? We have. We've actually done some studies on that, which gets into better to be perfect at one place where you understand everything, or better to have a distributed network of these things all over the world and start using the statistics of all the different atmosphere corrections and atmosphere correction retrievals and so forth, and get your sample size up super fast. I'm mixed opinion on it, frankly, but there are good arguments on both sides. Because one of the arguments for using one vicarious calibration site, then you use Buoy for a validation site independently, because as soon as you use the data for this, you can't use it for anything else. Yeah, so it seems related.
Yeah, sorry. If MOBI is hyperspectral, how do you, if you're trying to calibrate a satellite that has a wider spectral range?
Oh, yeah. So we know the spectral, so for these multispectral instruments, all of the filters are characterized so that we know they're bandpass. They're not like a rectangle, but there's characterization of the filter itself. So over a full spectral range, we know the signal across the full spectrum of their response. So typically in this case, you know, if it's a 443 filter, for example, there's a huge peak where light is let in at 443 and surrounding wavelengths, but sometimes there are leaks here and there. But nevertheless, because we have that hyperspectral information about the filter, and we have the hyperspectral information from MOBI, we can convolve the two to use MOBI to mimic what that single wavelength looks like on the instrument, on the satellite instrument. Did I explain that okay enough? Yeah, okay.
So for the infrared,
Yep.
Vicarious calibration, do you use like the same site as, for example, where MOBI is? Or you use more sites because you need connectivity?
No, we really, right now, we really just use this site. And so the matchups made here are totally independent from the matchups made there. The reason we use this site here is it's a very strong, it's in strong support of our assumption that there's no water leaving signal in the near infrared, and it's so far offshore you can make a reasonably educated guess on what kind of aerosol is there. So, but back to your thing, Anna. It's one of the debates we're going to have going forward with PACE. I'll show you the two instrument systems that we have invested in. One is a MOBI-like mooring, and the other is a series of radiometric buoys called HyperNav. And you can use all of them for vicarious calibration, but although I think what I might do is use Marinet for vicarious cal, and then get as many of those radiometric buoys in the field as fast as I possibly can. So now I have very, very high quality radiometry that I can use for validation. Now the other good news about MOBI is that through NOAA, they will continue to be supported off the coast of Hawaii. The MOBI-like system I'll show you for PACE is going to be deployed off the west coast of Australia. And I don't know what the status of this is, and I certainly can't speak to it, but there was talk about a MOBI-like system in the Med as well to support Copernicus, EUMETSAT, and ESA. So if something like that were to materialize, now you have 3 of them in very different places. And so we're starting to get data rich, which is pretty exciting. And then maybe folks like yourself can solve the debate on calibration at one place versus calibration at multiple places. And I have something I can show you that Sean Bailey did a long time ago that even some of the authors still are angry about. HyperNav has been funded through PACE so far. Yeah. Okay, so like I said, this is a single radiometric adjustment, and at this point, you know the temporal calibration has been applied. This is one way of kind of verifying it, but also a plot that shows you why we do not do temporal adjustments with vicarious calibration. So we look at the gain versus time. In this case, the black dots are what was accepted, and the white ones were the ones that were rejected. And here you want no, I mean, if you've done your temporal calibration correctly, there should be no slope here. But notice there is enough noise in here, you could probably draw some kind of line through this if you wanted to that indicated slope, or indicated change. We look at gain versus solar zenith angle, and we look at gain versus satellite zenith angle, because again, done correctly, all of this should be geometry independent. And in the end, you end up coming up with a series of singular values. So like, let's say we have 40 matchups, you have 40 Gs with a subscript I, you have 40 gains. Now we do the interquartile averaging, robust statistic rejection method to come up with a singular value that is applied universally at level 1B, top of the atmosphere. So for CWIFs, you can see we're actually adding some signal, like 3.7%, and on and on and on. I will note again, this is fixed at 150 matchups in this plot, and then there's some statistics around it as well. So let's go into some just show you some sensitivity analyses. Yeah, Luke. It's applied, it's in there. It's applied inside that level 1B to level 2. Mir, fact check.
Yes,
Sorry, I just mean to.
the process using some gas, the level 1 rate that will have.
Right, because you can put in L2 gen your gain factors if you want to change them. So yes. All right. Thank you, Amir. Sorry. All right, so in this case, what we're doing is we're doing what you're not supposed to do, but we're verifying that we did the process right, which is to take all of those gain matchups and then run the forward process at MOBI and just see that if our ratio is somewhere around unity in this case. So no, I'm sorry, that's not what you're looking at. We do that, but I'm not showing that. This is if we take what was our holdings in CBAS at the time, which is our bio-optical data archive. I didn't see the words, I didn't recognize the words deep water there. All of the matchups that were in water of 1,000 meters or more. And the reason is we didn't want to do this verification near the coast where the water gets more complex, as does the atmosphere. So anyway, nevertheless, we have varying numbers of matchups. The reason there are differences here is not every instrument that was deployed in the field at the time had all the same wavelengths. It's not like some got excluded and some didn't. There are just some instruments that at the time didn't have a 512 channel. But anyway, just for reference for the sensitivity analyses, here's pretty much the stats that we had at the time. For reference then, we ran that same series of deep water matchups with no vicarious calibration applied. And this is kind of the take-home message why we do this. And just look how much worse everything gets, including the number of failures. I mean, without a vicarious calibration, the system really does start to fall apart. That was repeated, doing only the near-infrared calibration to test the sensitivity of that. And you might get the matches back, the number of samples back, but the stats are still pretty garbage. So that really is just showing you some justification for doing the whole thing.
The 670 is a bit long.
Yeah, it's such a small number in deep water. He shouldn't have even shown it, I don't think.
Oh, yeah.
It's just a bunch of statistics on a teeny tiny little number. Okay, so you see, this is what I just showed you, just to share some sensitivity analyses. Let's see, this one was choosing a different aerosol model during the near-infrared calibration. So the gains change a little bit, but the statistics don't change a whole lot. This is the same for picking a different aerosol model and repeating the process. The reason I included this is, one, let you know that these kinds of sensitivity analyses can be done and are valuable. But at least for me, in having not thought about this for a couple of years, but when I was putting the presentation together, I was like, what do I want to say here? I think what it really tells me is that the system is insensitive to your, if you're a little wrong in your assumption that you know what the aerosol model is in the near-infrared and the South Pacific gyre, you're not going to get hurt too badly. And then in this case, what we're doing is saying that our assumption of a gain of 1 for 865 is a bad decision. And I'm saying bad, I mean, we're doing our best. And again, so in this case, we raised it by 4%. In this case, we lowered it by 4%. And there are some variations here that you can see. But I mean, honestly, telling these numbers apart is, tilting at windmills a little bit here. You would be picking and choosing, in my view, fairly arbitrarily of which is the best version. And so I think what this is telling me, with one caveat I'll show you later, that has only recently been revealed, is that the choice of 1 there is fairly robust. But I'm going to break that in a second. I'll break that statement in a second. Okay, so there were questions about, what if you only have one MOBI? What if you want to do something else? So in our case, we have done some exploration of alternative sources of what we're calling truth here. The first is we used a ocean biooptical model, meaning we're faking the data. And the second is we were using other data sources. The reason that I'm bringing these up is to address two different questions. The first is, if you don't have matchups right after you launch, what do? Do you sit and wait? No, in this case, we're going to use fake data. It'll be better than not doing a vicarious calibration at all. So we're going to launch in the first 6 months. We're probably going to use a biooptical model just to kick the tires and try to understand the performance of the instrument and the gain capability. And then the second one is, again, does it have to be MOBI? Could it be something else? And what happens if you combine data sources? Just to give you a general sense of the differences in the gains you would derive. So the way we do the model is, and I won't belabor this, but there are certain parts of the world where there are a ton of chlorophyll retrievals, and so we came up with seasonal averages of chlorophyll behavior with time in Bermuda and Hawaii. And then we took the Clearwater model of Andre Morel and used it to take a chlorophyll measurement and come up with a hyperspectral remote sensing reflectance. And you could do this with hydrolite, you could do this with a number of other biooptical models, whatever you want.
When you say long-term partial record, you mean in situ or?
Yes, I'm sorry, an in situ. Yeah, so both of these sites are NSF JGOFS institutions where there have been people going into the field for 20 years collecting filter pad samples of chlorophyll and putting them in public databases. And so now I can accumulate all of their chlorophyll and then do something like this, which is, take all the different years that I found, look at it as a function of day, year, and then squint my eyes and say I see a relationship. And then I could take that solid line going through here or that solid line going through there and say, that's a good enough chlorophyll value representing the average over time, and then put it into a very simple quasi-single scattering approximation of what the world should look like in radiometric and color standards relative to a chlorophyll signal. Okay, and so in this case, this is the percent difference between the gain you'd calculate at MOBI at the time and the gain that you would calculate using the biooptical model. And as you can see, in all instances, except for a few, it's less than 1%. What this translates to, if you look at MOBI-derived chlorophyll in our public database versus model-derived chlorophyll, and what I mean here is, if you look at all the matchups that we have and you run the matchups using the MOBI gains, you get one chlorophyll value. If you take all of the matchups we have and calculate satellite-derived chlorophyll using the other gains, you get another value. And you can see that the dynamic range does follow, but there's a little bit of a bias in it, and we'll come back to that in a second. Other sources of data at the time, this is AeroNet. You've seen that before. You've seen it in person. But there are AeroNet OC towers, so you have an AeroNet station where you're looking at the water. They're incredibly valuable. They will be used extensively for our validation early in the mission. But there's a lot of other ways you can collect data. And anyway, we went through the thought experiment of taking Busol, MOBI, and all of these other data points where we had radiometric measurements in the field, in the water that we thought were of value, and we calculated gains using them. And now you can see that generally speaking, they track with what we were able to derive from MOBI. If you run that chlorophyll thought exercise again, where you take your chlorophyll matchups with gains over one way, gains versus the other way, then, okay, you can see that the dynamic range behaves, but now you have a slope. All right, so the reason I'm showing you this stuff is twofold. One, hey, there's a lot of ways to do this, but two, and this gets into, do we use multiple sites or do we use one site? Whatever your gain calculation becomes, since it is an absolute adjustment to your last final fully calibrated value, it influences what your water leaving values will be. It influences what your AODs will be. If you change them, even these little changes, you are going to get a different answer in your derived products. It might not be a big answer, but it's going to be a different answer. And this is where the others on that paper come back and saying, I don't want a different answer because I don't trust their radiometry, I trust my radiometry, it's the best. So it's a little bit of a religious debate here, but it's an interesting one. And a lot of the changes we see here, you can't see in typical performance assessments. Like if I show you the chlorophyll matchups, which you'll see later maybe, it's such a scatter of data. Like our validation is 2,000 chlorophyll matchups for CWIS, but in log space, there's a huge slug of data. You don't see little differences like this, but you see it in your time series, or you see it in your little neck of the woods. So it's just something to be mindful of. All right, so what do we do looking forward? Here's a couple of things that are on my mind at least. The first is Brian Barnes at a USF, and this is where we're going to pick at that assumption of 1 as a gain at 865, maybe not being so awesome, comes into play. He's written a couple papers recently. They're listed here for your reference. Mir, if I screw this up, please help me. But what he has revealed is that your choice in 865 gain can actually impart a little bit of a time series in your retrieved values, which I still have trouble wrapping my head around, but the math supports it. So, okay, we got to think about that. And in fact, I believe in the reprocessing that we're doing now, we're using this adjustment, no? Yeah, I did. You're on camera, you're on the record. You got to get this right. We're not sure. So, another thing that's interesting to me, oh, sorry, Penguin.
It's a 5% gain change of A65. It's kind of a hypothetically hot, right?
This would be
That's 5%.
raise it by 5% or lower it by 5%.
Yeah, I mean,
It's on the high end of what you would expect, right? I think so. But let's just say that hypothetical change can impart a 6% seasonal cycle there. In your and these are retrieved remote sensing reflectances
what different wavelengths.
for different wavelengths. The different colors are different wavelengths. The papers will explain it all. So this is not an ego trip. This is actually something that interests me, and we mentioned line height before, but the reality is line height is nothing but curvature. This is just another fancy way of calculating a line height. This interests me for two reasons. One, we do individual calibrations of our wavelengths with zero consideration of the wavelength next to it. So 412 is calibrated by itself. 443 is calibrated by itself. They're all calibrated by themselves. We never, except for this one exception, have ever looked how they perform together. So that's fine for MODIS, spheres, CWIFs. We're going to be hyperspectral. How are we going to do our vicarious calibration? You saw yesterday there are 239 bands. We're going to calibrate them individually? Amir, are we going to calibrate them individually? Sorry, I'm teasing you because you're right in front of me. We don't know yet. So one way of looking at how band-to-band performances shift is through spectral curvature. So Rick Stumpf came up with this idea where we could calculate a spectral shape, which is basically just looking at peaks and valleys over a central wavelength. So in the case of, say, 443, your spectral shape at 443 would use your measurements at 412, 443, and 490. And so we had a thought experiment over MOBI where if you look at the spectral shape over time, you have in black dots the spectral shape from MOBI itself, in the blue line the spectral shape from CWIFs, and in red the spectral shape from MODIS Aqua. This is after vicarious calibration. These are the products that you would get off the street. And then if you start looking at the ratios of satellites to MOBI, you see that there is one pattern for CWIFs and a different pattern for MODIS, and it's very, very subtle. But if you look at the ratio of Aqua to CWIFs, you can see that they aren't necessarily agreeing here. And we've never adjusted for this. But nevertheless, maybe this is a tool in the toolbox to start looking at hyperspectral information. We don't know yet. Yeah?
For HICO or like Prisma, are those bands all calibrated independently?
I'll be honest, I don't know.
Yes.
They are.
For HICO, they were independently calibrated using the same procedure.
And for the record, I adore this man, so I'm just picking on him because I'm comfortable with him. Okay, wrapping up, just to give you a glimpse of what the two PACE Vicarious Calibration systems are currently look like. So right now, NASA headquarters using PACE Flight Project money has funded 2 instrument programs. They are getting ready to begin their 3rd year. They were competitive. The first is called HyperNav. It is generally out of Seabird Scientific. The PI is Andrew Bernard, who was at Seabird, has recently left for Oregon State. Nevertheless, it is a radiometric float, so something like that. Small, portable, it profiles. So what you gain from this is actually a high-resolution vertical profile. Fairly long duration, and in principle could be commercialized, which is really exciting in the sense of, hey, let's democratize this, everybody gets one. Yep.
Are those tethered or are they mobile?
These are, you could carry them around, you throw them off boats.
No, I apologize. Once they're deployed?
No, it's like BioArgo, they're Lagrangian, they just float.
Okay.
Yeah. So there's some really interesting modeling studies here. So part of this proposal, which is a great question, is you probably want to retrieve them, right? Like you can't do the post-cal if they just go away forever. And they're very hard, you don't want to be chasing them either. So the physical oceanography and the environmental modeling and hydrography that has gone into this, they're actually looking for these sustained eddies where they can deploy them, leave them out there for high duration, and then generally know the area. It's really cool. And I think they either just got back from Crete or maybe still there. But when I saw one of the co-Is on this a couple of weeks ago, he actually showed me the map, and the modeling was so good, you were just watching the buoy doing its thing in one little part of the ocean. So what they do is they basically park super deep to get rid of any kind of possibility of biofouling, and then they rise, they do their thing, they transmit data, and then they go back down.
Yeah, but I suspect that they look for eddies, particularly where Emmanuel wants to go.
Without question.
So they're deploying them in carefully chosen spots.
Yeah, you could deploy them anywhere you want, but this is increasing your chance of recovering it.
He likes to swim with them.
Oh yeah, he does. All right, then my last slide. Okay, so this is going to be the Moby follow-up with Moby Legacy. So that's Moby again, but Marinette. So again, University of Miami is doing this. It's a radiometric buoy. It's a 3-arm buoy again, but it has been upgraded to use far better technologies. It can now fit in a 20-foot container so that it can be shipped rather than this behemoth that lives on a boat. Still 3 fixed arms and still long deployment, but in this case, like I mentioned previously, and actually all eyes on Riley back there. He's part of the Marinette team. It'll be deployed off of the coast of Perth, Australia. So am I messing anything up, Riley?